expected value is a calculation which tells us if we look at all the potential outcomes of an experiment or some sort of probability situation, what are we most likely to have happen? Expected value can be useful in games like with gambling and odds. Like, for example, let's say that there were 4 sports teams and we had probabilities that they're going to win a championship. Like, say the Lakers were at a 30% to win the championship, the Nets were at a 30%, the Warriors were at a 20%, and I don't know, what's another decent team? I'll just pick one at random. The Celtics were 20%. So basically, let's just say there are only 4 teams in the NBA, and we had their most likely probabilities that they would win the championship. If we had the betting margins for how much money we could get for betting against those teams, we could see, well, let's say that I put a $1 bet on each team. What would be the expected money I get from these bets? And like I was saying, usually odds are set up against you to where your expected value would be negative, meaning that you'd be losing money if you bet no matter what. Obviously, if you get lucky and you choose the right team, which, some people say it's not luck. I mean, like some people do bet on sports for a living, but it's a very volatile, volatile job, which is subject to a lot of entropy. And anyways, I'm trying to not get off topic. Let's go ahead and look at an example of how we could calculate expected value and check out kind of what that means. And let's return back to the problem from class where we're looking at Billy pulling his toy cars from his shoebox. So in his shoebox, he had 5 Hot Wheels, 2 Micro Machines, and 3 Matchbox cars, if I recall correctly. And let's say that Billy designed a probability game to play, or a betting game where, and this is probably not an example you want to use with children because it might encourage them to gamble. But basically, he's going to charge his friends $1 to play this game. And he's going to say, okay, you can pull a car out of my shoebox, and depending on which car you pull, I'm going to give you money. And so basically, if they pull out a Matchbox car, they're going to win $2. If they pull out a Micro Machine, they're going to win 50 cents or 2 quarters. And if they pull out a Hot Wheel, they're going to win 10 cents. So Billy's kind of come up with this game where he'll pay them out based on what they pull. And obviously, people might be drawn into this at the chance of winning money from the game. But the question is this game favorable or non-favorable, or is it a game where you're actually going to be making money in the long run? Like if we looked at the law of large numbers and kept running this experiment, what would happen? So basically the idea is if we use the true probability of each outcome and multiply by the payout, we could check what the expected value is from running this experiment. And the last question it asks is this a fair game and should the classmates play? And basically that's the whole point of expected value, to sort of see what is an average outcome based on, it's sort of like multiplying each outcome by each respective probability. So in this case, pulling out a Matchbox, and it's probably worth reviewing the probabilities of each outcome. So the probability that they would pull out a Hot Wheel was 50%, because there were 5 out of 10 Hot Wheels in his box. The probability that they pull out a Micro Machine was 20%, because there were 2. And the probability that they pull out a Matchbox was 30%. And so we need to know all those probabilities. So you could call that P1, P2, P3 in this particular notation. I'll go ahead and rewrite it like that. The probability of each outcome occurring. And as the definition states, you need to take the numbers of the potential outcomes and multiply by the respective probabilities. So like in this example, if they pulled a Hot Wheel, they won a dime. So they got a dime. So basically A1 would be 10 cents. I'll just put that as 0.10. If they pulled out a Micro Machine, they would win 50 cents. And if they pulled out a Matchbox, they would win $2. And now if I multiply all that together and add it all up, that would give me my expected value. So I'll go ahead and say E. And notice that they use E once again, even though they use E for event. Not to be confused, this is not a set. This is a singular number calculation. But I'll go ahead and just call it EV so we're not reusing our variables in poor ways. But yeah, so P1 times A1 would be 0.1 times 0. I'll do it in the same order that the formula is written. I'll do A1 times P1. So essentially, and I'll kind of talk about the common sense of expected value as we do our calculations, but first let's just fill it in. So then we have A2 times P2, which was 20%. And then we have A3, which was $2 payout for a 30% Matchbox. And we could now determine the expected value. So essentially what I'm looking at is how much money did a kid pulling from Billy's shoebox make, and what was the probability of that actually happening? And this kind of makes sense because this gives us an averaged amount of dollars that we're going to make from this game, for lack of a better term. So if we do 0.1 times 0.5, that would be 0.05. So essentially my expected value of that one event in the case that a Hot Wheel was pulled out was only 5 cents, because you only made 10 cents anyways, and that it's only going to happen half the time. Then for the event of pulling out a Micro Machine, that would be, you get 50 cents, and that was only 20% of the time. So 5 times 2 is 10, so that would give us 0.1. Our expected value for that particular part is only 10 cents, because we're only going to be getting those 2 quarters 1/5 of the time. And then the last outcome, which is the most profitable event, which if we were the kid, we would be hoping that we would pull out the I can't remember, the Matchbox, which only would happen 30% of the time, but that would give us 2 times 0.3 is 0.6. And basically I'd be making 60 cents expected from that particular event, because only 30% of the time am I going to get the Matchbox, and when I do, I'm going to get $2. And anyways, if I add all this up, this gives me the sum of all the expected values of each outcome, which would be, it appears to be 75 cents. And what that means is that if I play this game, that's going to be what I would on average expect to get from the game. Because, 30% of the time I'm going to get $2, 20% of the time I'm going to get 50 cents, and 10% of the time, 50% of the time I'm going to get 10 cents. So if we kind of add all of those together, I don't know, this sort of just makes intuitive sense to me, but if I add all that together, usually I'm going to get 75 cents. Obviously, if I actually play the experiment, I could see, and we could do an empirical expected value by, say, trying this 10 times, seeing what our payout would be, and then dividing our actual payout divided by how much money we put in. And also, the definition of a fair game is a game in which the expected value is 0. Another thing we need to take into account is what is the cost of playing this game. So since the cost was $1 per pull, really, I'm expecting to lose 25 cents each time I play this game. And you could build that into the formula by saying, add up all of the expected outcomes. And I mean, technically we'd say, well, event 4 is the fact that I had to pay $1 and that I had to do 100% of the time. But, I think I like a little bit more of a common sense approach to this, where this is my expected payout. And since it cost $1, on average, I'm going to be losing 25 cents. So no, his classmates should not play this game unless them losing money is, worth the fun of doing this. But that's kind of always the claim with gambling, is that, it's a game. It's supposed to be fun. And that's why we're setting ourselves up to lose money.